Yeah, maybe I need to excuse myself.
Before you start?
Nope. Let's see if I can make this happen. Yeah, it's looking good so far.
Yes, you did.
There. Okay. Now, is there a way to turn off all these guys on the side?
View options. Yeah, at the top of your window, view options.
Window view options. Okay, mute, stop video, participants.
You want to go down to where it says hide video panel.
I don't have a hide video panel. I have more, which may, oh, there it is. It's under more. Hide video panel. There we go. Perfect. Okay.
All right.
So I'm John Eisenberg, K6YP, and today I'd like to tell you about just an amazing piece of equipment. It's a very low-cost vector network analyzer, and hopefully about halfway through this presentation, everyone will know what a vector network analyzer is and why you might just want one. So in 1969, I was a brand new microwave engineer at Watkins Johnson Company in Palo Alto. I was fortunate to have the new HP 8410 VNA system on my bench. It covered from 100 megahertz to 2 gigahertz, and then from 2 gigahertz to 12.4 gigahertz in a couple of bands. It was the very first vector network analyzer. It was about a yard high, and it weighed at least a couple 100 pounds. But it was a tremendous advance in microwave instrumentation. Its competition was the slotted line. If anybody remembers those, it took forever to make a measurement, and you did it point by point. The HP 8410A system sped up measurements by a factor of 50 times. The VNA displayed swept data on the Smith chart. Using it made microwave measurements almost intuitive. The 8410A system hooked me on RF and microwave engineering. But the cost of the silly thing was $12,500 in 1969 dollars, which was nearly twice my annual pay. Present day VNAs cost between $10K and $50K. In 1969, a ham couldn't even dream of owning one of these. So fast forward to 2020 and meet the VNA, the NanoVNA-F. It's a little black box. It has a 4.3-inch color screen. It has a solid aluminum case, which shields the machine from external RF sources. It works by emitting a reference signal, which is swept over frequency, and looking at the reflect signal's magnitude and phase back into port 1, and also the signal leaking through the device referred to E-reference in terms of magnitude and phase, so that you can actually measure the input impedance of something plus its gain and transmission phase. You can kind of see here, port 1 is open, it's an open circuit, and you can see on the Smith chart that that open circuit is right where it ought to be on the Smith chart at 1 at 180 degrees, and that the return loss is 0 dB. The instrument's made in China by a company called Dipole. The design and software engineering was done by Leon Huang, BH5HNU. It covers 50 kilohertz, taking you way down into the IF frequency range, all the way up to 1.3 gigahertz, which is something that would make K6YP happy. And of course, it's a vector network analyzer. It measures magnitude and phase. The latest version is 3.1, and it has 3 buttons on the side. And keep in mind what that looks like, because I'll talk about that in just a bit more. But the most amazing thing about this instrument is shipped to your door, mine cost $95. So what can you do with a VNA? Well, you can measure your antenna's impedance, and if you want, plot it on a Smith chart. You probably don't want to do that. So you could just plot the SWR of your antenna versus frequency. We're using the same measurement to do that. You could measure some unknown inductor in your junk box, and you could measure it at the frequency you plan to use it at and actually know what the inductor is. You could measure the input and output impedances, gain, insertion loss, and transmission phase of an amplifier or filter and plot it all versus frequency. The VNA covers from 50 kilohertz to 1300 megahertz and can store up to 5 sets of calibration data. All this for about $100, and it's almost as capable as one of the modern 30K Keysight or HP vector network analyzer. This is not your old MFJ 259. So let's start with what's in a number. What does the VNA actually measure? Ordinary numbers are scalar, not vector. 6 is a scalar number. So is 376.73 and a bunch of garbage, the characteristic impedance of free space. A scalar number is given only by its magnitude. SWR is scalar, so is gain in dB. Both only have a magnitude. A vector is a complex number, such as 3 plus J7. Impedance is a vector quantity, like Z equals 47 minus J17 ohms. A vector has both magnitude and direction. The NanoVNA-F measures vector quantities, but provides output in both vector and scalar forms. A vector has a magnitude and angle, and also real and imaginary parts. Many things in electronics are best represented with complex numbers. Impedance is a complex quantity. For example, the impedance of a certain 33 ohm wire wound resistor is 33 plus J26 ohms when measured at 10 megahertz. 33 ohms is the real part, or resistance. 26 ohms is the imaginary part, or inductive reactance, a positive number. Capacitive reactance is a negative quantity, like minus 14 ohms. J is the way electrical engineers write a complex number. J replaces the old I that we all learned in high school. Another way to express complex quantities is in polar form. Polar quantities are given by a magnitude and an angle. This is very useful for plotting polar impedance data and for plotting reflection coefficient measurements on the Smith chart, which we'll get to in a bit. For Z equals 33 plus J26 ohms, the magnitude of Z is the square root of R square plus X square, or the square root of 33 square plus 26 square, which is 42 ohms. The angle of Z is an angle whose tangent is the reactance divided by the resistance, or 26 divided by 33, and that is 36.23 degrees. To convert magnitude and angle back to real and imaginary parts, real is the magnitude times the cosine of the angle, and imaginary is the magnitude times the sine of the angle. Nasty stuff. Fortunately, all that math gets done inside the NanoVNA, so you don't have to do it. So let's just quickly review. A scalar number has magnitude but not direction. Pi is a scalar quantity, whereas a vector has both magnitude and direction. Here we have a vector pointing in a given direction given by its magnitude and its angle. And you can see that the imaginary part is the magnitude times the sine of the angle, and the real part is the magnitude times the cosine of the angle. And if you forget that, which I wouldn't forgive you, the VNA will remember it for you and do the math correctly. So the first word in vector network analyzer is vector. Our 33 ohm wire wound resistor is not a pure resistance. Its impedance is 33 plus J26 ohms at 10 megahertz, which looks like a 33 ohm resistor in series with a 26 ohm inductive reactance. So the impedance of the resistor is a complex number or a vector quantity. The VNA-F measures vector quantity. The inductive reactance, by the way, comes from the turns of resistance wire, making up the 33 ohm resistor. The second word in vector network analyzer is network. Networks are black boxes with ports. A one port has two pairs of terminals that allow connection to the outside world. A port could be a pair of screw terminals or coax connectors, such as an SO239. Our 36 plus J26 ohm impedance is a one port. It has a single pair of terminals. An amplifier that has a single input and a single output is a two port. It has two pairs of terminals. And today we'll mostly deal with one and two port networks. The last word in vector network analyzer is analyzer. A vector network analyzer is an instrument that can accurately measure the characteristics of one, two, or n port networks and express the results in many forms, both vector and scalar. It can characterize one port, such as antennas and loads, and two ports, such as filters and amplifiers. And it can present the results in terms of complex impedance, polar gain and phase, SWR, return loss, and more. So here's a one port. Let's look at how it's characterized. A one port is simply a box that has a pair of terminals. And that pair of terminals, in this case, is the reference plane that we're going to make the impedance measurement. And we'll talk a little bit more about that in just a moment as well. We have a 50 ohm generator, which is a voltage source in series with a 50 ohm resistance. And we have a length of 50 ohm transmission line feeding the one port. The forward wave travels from the source toward the one port, which then reflects some of it back as the reflected wave. And the amplitude of the reflective wave at the reference plane is E reflect, and the amplitude of the forward wave at the reference plane is E reference. So the reflection coefficient is E reflect divided by E reference, sometimes called S11, or the input reflection coefficient of the device. Once again, the reflection coefficient, gamma, is E reflect divided by E reference. It's a complex quantity because E reflect and E reference have a phase difference between them, making this a complex polar number. It's measured in a 50 ohm system because the generator impedance and the transmission line impedance are 50 ohms. E reflect and E reference must be measured at the same point on the transmission line. This point is called a reference plane, and gamma N may also be called S11. Impedance may be calculated from gamma, the reflection coefficient. Z, the impedance looking into the one port, is given by Z0, 50 ohms in this case, times 1 plus gamma divided by 1 minus gamma. Gamma is a complex number, so as a result, Z is complex. And of course, everything is defined in a 50 ohm system where the generator and the characteristic impedance are 50 ohms. SWR is scalar because it's defined as 1 plus the magnitude of gamma, just the length of the vector, divided by 1 minus gamma, the length of the vector. So SWR is a scalar as a result, also defined in a 50 ohm system. Another way of talking about the input properties of the device is a quantity called return loss. And return loss is simply how many dB down the reflected signal is versus the forward signal, usually expressed in dBs. And that pretty much sums up return loss. And once again, all of this math is done in the VNA, and that's really about all one needs to say about a one port. The two port's a little more complicated. This is the view of a two port as seen by one of those $30,000 network analyzers that has the capability of flipping the source around to the back side of the device and flipping the load back around to the front side of the device. So we can measure all of this in one gulp. We have an input forward wave and a reflected signal that gives rise to E reference 1 and E reflect 1, which gives rise to S11, which is the ratio of E reflect to E reference. It also gives us an S21 term, which is the voltage gain from port 1 to port 2, which is the ratio of E reflect 2 to E reference 1. Similarly, you have an incident forward wave and a reflected signal and a transmitted signal, which give rise to S22 and S12. But nobody's got 30K in their pocket, and so the VNA, the NanoVNA-F, sees the two-port in a slightly different way. We can only measure S11 and S21 at a time by looking at the ratio of E reflect to E reference and E through to E reference and their respective phase angles. But you can get all four parameters by simply unscrewing the device from the network analyzer, turning it around backwards, and measuring S22 and S12. And by so doing, you save about 29.9K in the process over the 30K price of a real commercial HP VNA. The VNA-F measures all the same quantities at port 1 of the 2-port that we've already discussed in the previous 1-port case. In addition, the VNA can measure gain or loss from port 1 to port 2 of the 2-port, along with the transmission phase along the path from port 1 to port 2. Both can be plotted against frequency. And again, by reversing the 2-port, its reverse gain or loss and phase may be measured, along with port 2's input impedance, SWR, or return loss. So looking at the 2-port transmission characteristics, in other words, S21, the gain or loss from port 1 to port 2, we're measuring gain and phase of the 2-port by looking at E through divided by E reference. This is a complex voltage gain. E through and E reference are measured in a 50 ohm system where the source impedance, the load impedance, and the transmission line impedance are all 50 ohms. Complex voltage gain is also called S21. Power gain is equal to 10 log the magnitude of E through over E reference, a very useful quantity measured in dB. It's of course a scalar, and what it expresses is P out over P in, what we all look at normally as gain. Voltage gain is the ratio of the output voltage divided by the input voltage, and it's 20 log the magnitude of E through divided by E reference, also expressed in dB and also scalar. And of course, both of these are measured in a 50 ohm system. Phase is the angle of E through divided by E reference, or the angle whose tangent is E through over E reference, and it's also scalar. Gain and phase, however, taken together are S21, a polar vector quantity characterizing the transmission through the device, again in a 50 ohm system. S21 is usually expressed as a power gain magnitude in dB and an angle in degrees. But fortunately, as before, all the math is done inside the VNA, and going through all this nonsense really is meant to give you a feel for what the instrument's measuring, not how to do the calculations. Well, the last thing that we need to cover are reference planes. So here's a 2-port, and the reference planes just happen to be at these 2 red lines. And you need to connect the 2-port, which is the device under test, and the Cal standards at the 2 sets of reference planes. Why? Because if you calibrated the device at this reference plane and measured the device here, the phase would be different, which would upset the input impedance and also the transmission phase through the device. So it's very important when you're measuring something to understand where the instrument is calibrated and where you're actually making the measurement, which is where it was calibrated. Sometimes the reference planes are at the connector interfaces, and sometimes they're not. A coaxial device like a bandpass filter, say a 100 to 150 megahertz bandpass filter that has reference planes at the SMA connectors on the filter body, is a very, very simple way to define a set of reference planes. However, the standards that you get with the VNA turn out to be male. You need a set of female sex Cal standards. You can make them with female SMA connectors by soldering a short circuit across the back of the connector and open by leaving nothing on the back of the connector and soldering a couple of 100 ohm resistors in parallel to get a decent 50 ohm match. And with that, you can make a very nice measurement of a bandpass filter. Here's a slightly more interesting case. Here's a microwave transistor, which comes in a strip line package. It has two little legs that go to ground, grounding the emitters of the device. And it's got a base side and a collector side that are soldered onto these two microstrip transmission lines printed on this printed circuit board. And again, we've got a couple of SMA connectors. However, to measure the transistor accurately so that we could design with it, we'd want to have those reference planes located right at the outside of the transistor. And to do that, you need 4 extra fixtures. This one, which is the 5th one, and 4 others. The first one would be a fixture just like this one with a short circuit wrapped around to the back of the board and a short circuit wrapped around to the back of the board. That's the short fixture. Another one with these 2 lines open circuited. Another one with 50 ohm resistors to ground at both of these 2 points. And finally, a through where we saw out the transistor and replace it with a through that is the length from here to here and the length from here to here, and you lose the length of the transistor. This is actually how transistor S parameters are measured if you ever looked at a data sheet for an RF transistor. So just a quick comment on S parameters, because I've mentioned them throughout the talk, and I'll just quickly define them and then won't talk about them anymore. S11 is the input reflection coefficient, gamma 1, of a 2-port driven from and terminated in 50 ohms. So the source impedance, the load impedance, and the characteristic impedance of the transmission line are all 50 ohms. And it fully describes a 1-port. S11 is all you need to know. S21 is the forward voltage gain in phase of a 2-port in a 50 ohm system. S12 is the reverse voltage gain, also in a 50 ohm system. And S22 is the output reflection coefficient. You get these 2 by reversing the device. These 4 complex S parameters completely characterize a linear 2-port. But it's critical to remember that the cal and measurement reference planes must be the same. So, what can a under $100 VNA do for me? We can measure everything that we've talked about to this point in the talk. You can measure scalar and complex quantities, reflection coefficient, impedance, SWR, return loss, gain, loss, transmission phase, S parameters, and you can sweep them all across the 50 kc to 1300 megahertz frequency range. And you can plot the data either on the 4.3-inch screen of the NanoVNA or on your PC. You can perform conversions between measured data, such as converting a complex reflection coefficient into a complex impedance. And you can do all these things with amazing accuracy. So now we know what the VNA-F can measure. What about its specifications? What's in it? How does it work? And how do we use it? Well, the first question is, what NanoVNA-F should I get? And the reason that I picked the NanoVNA-F is really because, first, it has a 4.3-inch screen that you can actually see outdoors, where some of the 2.8-inch ones are very, very difficult to read in a bright sunlit environment. Second is it comes in a solid aluminum case, which means it's well shielded against RF signals in the environment. This one is the newer version 3.1, which has, at this point, the 0.2.0, which they released yesterday, as firmware. And you can easily get that firmware, and I'll mention how in a bit. This is the one with the 3 buttons, and this is the one I recommend. The older 2.3 has a rotary dial. You can see it here. And the problem is that rotary dial has been less reliable than the buttons and often breaks. So here's the key specifications of the instrument. It covers 50 kilohertz to 1300 megahertz. It's actually usable to 1500 megahertz. The frequency stability is an amazing plus minus 2.5 parts per million, fully synthesized. It can sweep 101 data points, which kind of says that you don't want to sweep that entire frequency range of 50 kilohertz to 1300 megahertz, because 101 points really isn't enough to really zoom in on a narrowband device. If you want to do that, you can display the data on your PC and have the PC control the instrument, and you can get 10 times more frequency points by doing that. You can have up to 4 traces, all types, both reflection and transmission. You can have 4 frequency markers. You can have 5 sets of calibration data. You can display log magnitude, linear magnitude, phase, polar, Smith chart data, SWR, impedance, resistance, reactance, almost anything you can think of. The device contains a 5 amp hour battery, which lasts over 8 hours outdoors. It has a 4.3-inch diagonal display and displays 800 by 480 pixels. The dynamic range of the VNA is really quite spectacular. Across the 50 kilohertz to 300 megahertz range, you can see down 60 dB in reflection, and you can see down 70 dB in transmission. In the 600 megahertz to 1 gigahertz range, that drops to 40 dB in reflection. But a 40 dB reflection is a reflection coefficient of 0.01 or an SWR of 1.02. That's pretty darn good. One thing to be cautious of is the maximum power allowed into either port of the VNA is 100 milliwatts or plus 20 dBm. So how does this really clever instrument work? First, I'll try to say it in words, and then we'll look at a picture. In the VNA, there's a stable dual frequency phase lock loop signal source, which can be stepped over frequency. It produces 2 signals that are spaced 5 kilohertz apart. One signal is E reference, and the other signal is a local oscillator signal. These signals are digital waveforms with fast edges, and therefore they have harmonics, making them useful up to approximately 1500 megahertz. The E reference signal is connected to port 1 of the device under test. The device under test reflects a signal E reflect back to a high-performance Wheatstone bridge, which separates E reference and the E reflect signals. The individual E reference and E reflect signals are mixed with the local oscillator frequency in separate mixers to generate a pair of 5 kilohertz IF signals representing E reference and E reflect. And the ratio of E reflect to E reference is used to determine the port 1 complex reflection coefficient, gamma in or S11. This is used to find the impedance resistance, reactance, return loss, and SWR of port 1. The E through signal passing through the DUT is also mixed with the local oscillator to generate a 5 kilohertz IF signal. The ratio of E through over E reference is S21 and is used to determine the gain and phase of the device under test. These three signals are amplified and digitized and further processed by the microprocessor in the instrument to generate the desired plots, which are displayed on the 4.3-inch screen. Here's a block diagram of the NanoVNA-F. Port 1 and port 2 are on the device under test. And so the phase lock loop generates a signal between 50 kilohertz and 1300 megahertz by using the harmonics of the signal source. And it's squirted out at port 1 of the device. The device reflects some of that energy back, and it appears in this mixer where it's mixed with the reference signal, the local oscillator signal, to generate the, I'm sorry, let's take that so I don't confuse you. The signal is squirted out into the device, and the reflected signal is delivered to the reflect mixer and is mixed with the local oscillator to generate a reflect signal at 5 kilohertz. Similarly, the reference signal is mixed with the LO to generate the reference 5 kilohertz IF, and the output coming from the device under test is mixed again with the local oscillator to generate the through signal. This component is called a codec, and the codec contains, actually contains more than 3, but it contains 3 amplifiers and A to D converters that digitize the voltages E reflect, E reference, and E through. Those are delivered to the microprocessor, which crunches the numbers and puts the final result up on the display. So here is the inside of the NanoVNA-F. The reflect mixer is hidden inside this shield, the reference mixer inside this one, and the through mixer here. Here's the little phase lock loop signal source and the crystal oscillator that controls it. This is the codec, and this is the microprocessor that does the number crunching. And the rest of the stuff has to do with battery management and also supporting the USB port. This is the dial type VNA-F, and this is the thing that you kind of want to avoid because it's been shown to be less reliable. Here's the battery side of the device, and this is your 5 amp hour battery. So how do you use it? Well, you set the frequency range by going to the stimulus tab, and you either set a start and stop frequency range or a center and span, for example, 100 megahertz plus or minus 20 megahertz, or you go to some CW frequency that you want to measure at. You calibrate it according to your actual needs. You select the display formats that you want to see. For example, the magnitude of S11 in dB, and you save the parameters for the next measurement that you want to do of the same thing in the 5 available registers. So here's how you actually do that. Here's the screen of the NanoVNA-F. You tap on the screen with your finger, and these little guys, tabs if you like, appear. The first one is display, which allows you to change the format, the color, the scale, or turn on and off traces. In this case, all 4 traces are present. There's a green dot right here, which is on the Smith chart. This is input return loss. This is S21 transmission phase, and this is the leakage from the open ports of the device. This one will let you set the markers. In this case, one marker is set. You can see it on each of the traces. The marker is at 50 kilohertz. Stimulus allows you to set the start, stop, or center and span frequencies, as well as the CW frequency. Calibrate is how you first reset and then measure the calibration standards. Recall allows you to recall measurement formats for something that you've done before. Configuration allows you to change the language to Chinese if you'd like. You can calibrate the screen, and you can also see the version of the hardware and software in the instrument. And this guy allows you to close it, getting you back to full screen operation. When you receive the vector network analyzer, you'll get this sheet of paper. First, you want to make sure that the firmware agrees with what you've got. And this is what we just saw on the screen of the instrument. And we could follow, for example, the stimulus down to here, and we can set the start, stop, center, span, CW frequency. We can pause the sweep, or we can go back to the main menu. I won't go through all of these, but you can see it's very easy to operate this device. This brings us to calibration. The internal hardware of the VNA is not perfectly accurate. If it's not calibrated, the accuracy is not going to be very good. But by measuring several accurately known standards, the VNA may be calibrated and corrected to yield very accurate measurements. The standards used are a coaxial short circuit, a coaxial open circuit, 2 precision 50 ohm loads, although one of them isn't 100% necessary, and a through connection. The calibration done with these standards is known as an SOLT calibration, short, open, load, and through. And here are all those things. Here's a SMA open, an SMA short, an SMA load. Here's a double male to make a through connection, or a double male to make a female through connection. And for some reason, they give you a right angle as well. Plus, they give you a couple of pretty decent RG316 Teflon coax jumpers that you can use to connect the device under test to the VNA-F. The whole thing is delivered in a nice plastic box, which is included inside a nice stiff cardboard box that does a really nice job of protecting the instrument. So here's a brief summary of the calibration steps. First, you open the calibration memory and press reset so that you flush out the old calibration. You open the calibrate menu, which is under it. You connect the SMA open to port 1, wait a few seconds, and then press open. And then you connect the SMA short to port 1, wait a few more seconds, and press short. You connect the SMA load to port 1, wait a few more seconds yet, and press load. And then connect an SMA load to port 1 and another to port 2, wait a few seconds, and press isolation. That second load isn't absolutely essential unless you're trying to measure a high isolation device. So if you don't happen to have a second load, just leave port 2 open. You connect an RF cable from port 1 to port 2 and wait a few more seconds and press through. Press done and save the data to one of the calibration registers 0 through 4. And there you are, you're calibrated. Okay, enough of the theory, let's measure something. And so we will. Here's a 2-meter bandpass filter, happens to be centered at 145.3 megahertz, and we're looking at it at 20 megahertz per division. So the center of the display here at marker 1 is at 145.3, and the span is 120 megahertz. This trace is the log magnitude of S21 at 10 dB per division. And so you can really see the characteristics of the filter over frequency. This guy is the SWR of the filter. At this point, at marker 1, the SWR is 1.22 to 1. And you can see that in the return loss as well, which is 19.76 dB. But the filter is a little bit crappy in that the return loss degrades to worse than a 2 to 1 SWR, or less than 10 dB return loss over frequency. You can also see that we're using calibration 2. In other words, we're stored in register number 2, and it's open, reflection, short, through, and isolation have all been run to set up the calibration. Here is the VNA measuring a short circuit connected to port 1 on the Smith chart, and we're sweeping across the 50 kilohertz to 1 gigahertz frequency range. And you can see that it's all balled up right at 1 at 180 degrees, which is a short circuit on the Smith chart. That is really a decent measurement. You couldn't do that with the old 8410 system back in 1969. Here we're looking at just a through cable, and you can see that the transmission from port 1 to port 2 is essentially 0 dB, as you'd expect, and the return loss is approximately 20 dB all the way up to about 800 megahertz, and a little worse from 800 to 1000. And you can see also that happening on the Smith chart, where the 800 to 1000 is happening right in this region, and the rest of it's pretty much balled up at 50 ohms. Here's a little trick measurement. We're measuring the polar pattern of a UHF Yagi. The Yagi is connected to the transmit port on the VNA, in other words, port 1, and an omnidirectional whip antenna is connected to the receive port. The VNA is set to a single frequency, and the UHF Yagi is rotated to capture the plot. A PC is connected to the VNA and generates the polar plot as the Yagi is rotated. So here's the polar plot, here's the Yagi, and down at this end you can see the whip antenna and a long cable between the Yagi and the VNA, which is located right here. Very slick way to measure the pattern of a Yagi antenna in the UHF frequency range. Here's an attenuator, a 20 dB attenuator. I'm measuring the loss of the attenuator on this trace, and this time I'm measuring from 10 kilohertz, which is really a little lower than the instrument is supposed to be used, to 1500 megahertz. And you can see that above about 1300 megahertz, the measurement turns sour. Here at 750 megahertz, I got 20.39 dB, which is right on. And you can also see the frequency accuracy we're getting, or at least the resolution we're getting. This is 750.005 megahertz. Here we have the input the input return loss of the device on the yellow trace. And you can see at 750 megahertz, that's 33 dB, or a very, very good SWR. And on the Smith chart, it's all balled up at 50 ohms. So that's kind of like an excellent test of the performance of the VNA-F. Well, something else that you can do with the NanoVNA is display the results and control the VNA using your PC, using NanoVNA Sabre software. This transfers the measured data from the NanoVNA to your PC, Mac, or Linux box. All three versions of the software are available. It allows up to 10 segments, as I mentioned before, of the measured data to be plotted. That's up to 1010 points, which gives you darn nice resolution. And this is free shareware available at github.com. You can display up to 4 separate plots at once. For example, a Smith chart plot, a log magnitude S11 plot, phase, and real and imaginary impedance all at the same time. You can average your data, and you can control the VNA from your PC, Linux, or Mac. And finally, it permits a customized data frequency range to be generated from a wider band calibration. It also does a bunch more things, but I'll leave that to you to find out what it can do for you. Did I mention it was free? So here I'm using that VNA Saver software to look at an 80-meter Windom off-center fed dipole. You can see that the return loss of the dipole is very good at the center frequency and degrades to crappy as all heck at not even the edges of the 80-meter band. And looking at the data, we see that at 3698.98 kilohertz, in other words, virtually 3700 kilohertz, the return loss is 30.866, the VSWR is 1.05, the parallel R is 52, and the parallel X is 17 ohms. As we sweep higher in frequency, we hit the green dot here. I'm sorry, as we sweep lower in frequency, we hit the green dot here at 3800 kilohertz, and we find out that we have about a 79 ohm resistance and 137 ohm positive reactance, which gives rise to about a 6 dB, 6.5 dB return loss. Even worse at 3500 kc, which you can see it's further out on the Smith chart. And the return loss is, gosh, it's 2.5 dB. But you can certainly see the characteristics of your antenna using the NanoVNA-F and the VNA Saver software. Here's another case using the same software. This is a one-port device which just happens to have two resonances. You can see we get very close to 50 ohms here, and we get very close to 50 ohms here and here. 50 ohms on the Smith chart is right there. And we have markers at 14.074, at 7.1, and at 46 megahertz. So here is the 7.1 megahertz marker. And if you look really carefully, you can see the 14.074, and even more carefully, you can see the 46 megahertz marker. We're sweeping from 100 kc to 52 megahertz. And if you look even more carefully yet, you can see the markers on the Smith charts. But the easiest place to see them is on this chart, which is R plotted in pink. And you can see the two resonances here and here. And this is X plotted in blue. Again, a very useful tool for analyzing the data. Well, I've probably fed you with a bit of a fire hose, so blessedly we're at the conclusion. And I think you can see that the VNA-F is a very useful tool for many of your RF measurement needs. It's far more versatile and accurate than most one-port antenna analyzers and many other nano VNAs. It's way less expensive too. Some of the antenna analyzers go up to $500. And remember, this thing costs $100 shipped to your door if you do a good job of searching the internet, and you can't pay much more than $150 for it. With its 4.3-inch touchscreen, diagonal touchscreen, multiple measurement types, solid aluminum case, ease of use, many supplied accessories, and low cost, this instrument is a joy to use, and you may want one in your shack. Beware of the nano VNAs in the $50 price range. They have 2.8-inch LCD screens and an aluminum case that are not as well made as this instrument. Well, that brings us to the point where if you have any questions, I'd sure like to take them on. And I'm going to stop.
John, what I'd like to do, if this is okay with you, because the questions, there may be lots of people that want questions. I'd like to get your permission here. I have 2 more items on the meeting, and then I'll adjourn the meeting. And that way people who want to stay and ask questions can have as long as they want. There'll be no interruption. Is that okay with you?
Works for me.
Okay, go ahead and stop sharing for the moment. And then maybe when questions start, you might want to bring